My name is João Miguel Santos, and it is a great honor to be here on behalf of this team to present you our work under the theme A Smart IoT System for Water Monitoring and Analysis. The work focuses on the architecture of a system that is being developed in the framework of the Internet of Things, IoT, for the smart monitoring of water resources. IoT-based systems, in particular those made with open-source hardware and software, like the one we aim for, have lower costs compared to traditional systems, making them suitable for replication and scalability. We will start with the motivation for this work and the problems it aims to solve. We will review some of the characteristics of IoT systems with a focus on environmental monitoring. We will follow with our proposed architecture for this type of system, and we will conclude with perspectives for future work. Water is a resource unlike any other, being an essential component of all forms of life. Its value and importance have always marked the need for its public administration and regulation. Not only the quantity, but also the quality of water is essential for the well-being and health of the population, requiring careful monitoring of water quality and the judicious management of water quantity. This is of particular importance in southern European countries, where droughts have made water such a precious and scarce resource, and it becomes even more important in industrialized countries where pollution, contamination, and the increasing demand for water exacerbate the problem, which becomes even more serious with climate change. Two of the 17 Sustainable Development Goals for the 2030 defined by the United Nations are the achievement of access to water and sanitation for all, and the urgent action to combat climate change and its impacts. However, billions of people still lack access to safe drinking water, sanitation, and hygiene, with more than 2 billion people living in water-stressed countries, worsened by the decline of natural wetlands and forest loss. And today, there are more than 100 countries which are not on track to have sustainably managed water resources by 2030, imposing the need to double the efforts and motivating the development of systems like the one we propose. According to the IEEE definition, the scope of an Internet of Things system varies from a small system which contains uniquely identifiable things to a system that interconnects millions of things with a capacity to deliver complex services. Smart environment monitoring, in which smart water monitoring can be included, catalyzes progresses in the capabilities of data collection, communication, data analysis, and early warning, in which machine learning and pattern recognition takes a fundamental role. Recent technological advances in sensors, microcontrollers, single-board computers, and communication technologies, with a significant drop in energy consumption and cost, have made possible to meet the growing need for environmental monitoring using systems with IoT-based architectures, in an approach that has been the subject of study over the past few years. Among the reasons for the rapid increase on the quantity of IoT systems is the availability of low-cost, energy-efficient, and powerful hardware for sensing, acquiring, processing, and transmitting data to the cloud. Ubiquitous equipment in these systems are microcontroller units, cost-effective devices that meet the real-time needs faced by IoT applications with the low power constraints of this kind of systems, including data acquisition and communication capabilities. Single-board computers have also become increasingly present in IoT systems. These devices, capable of running a full operating system, increase the capabilities of local nodes, namely by boosting the processing power and data storage, and may include multi-core graphic processing units optimized for machine learning. The proposed smart IoT system for water monitoring and analysis allows the acquisition of data at different locations along the water surface, at different depths and at different regular time intervals, with the aim of characterizing water quality and quantity for which meteorological conditions are required. Coupled with the machine learning and pattern recognition system and the information from other sources, the proposed system aims to provide the possibility to forecast future problems like biological or chemical contamination, or those arriving as consequences of climate change, and even to deliver valuable data for hydrological modeling. A layer-based diagram for the proposed architecture has the following characteristics. At the lowest level, we have the sources of data, water, physical and chemical parameters, and atmosphere parameters. The sensing layer comprises sensors, microcontrollers, and single-board computers. Sensors are responsible for providing a measure of the physical and chemical parameters from the surface water and from the surrounding atmosphere. Using data acquisition computing modules, communications hardware and software protocols, microcontrollers and single-board computers receive and transmit the collected data to the network layer, which is responsible to transmit data at a long distance to other network devices and servers. The network layer comprises the communication technologies and data transmission protocols. The choice of communication technologies is defined by the existing conditions of the data collection site, in particular the physical conditions, the availability of communications, and the type of power sources available. It can be the long-range, low-energy, LoRa transmission hardware or other communication technologies. It may even be the combination of more than one of these technologies. Data exchange protocols are responsible for communications with the service support and the application support layer. The diagram represents a series of application protocols like LoRaWAN, MQTT, HTTP, WebSockets, and CoAP, commonly used in IoT systems. The service and the application support layer represent services that enable IoT applications and services. It contains functionalities such as data processing, analysis, apps, and storage, as well as specialized functionality per application and service. This level comprises the treatment, analysis, and storage of the collected data. The data must be stored and used intelligently for smart monitoring and actuation. Data is stored in databases, and blockchain technology is used to keep data integrity. The top level includes the visualization of the collected and processed data, interacts with users through screens, forms, menus, reports, and so on. It is the most visible layer of the application. It defines how the application looks, and comprises the data storage, analysis apps, and visualization layers. This level comprises the treatment, analysis, and storage of the collected data. The data must be stored and used intelligently for smart monitoring and actuation. To extract high-level knowledge from the collected and stored data, the information quality is important. The quality of the information from each sensor depends on error in measurements, precision and accuracy of the data collection, the device's environmental noise, the digital conversion of the observation and measurements, and even the pre-processing made at the data acquisition level. IoT systems generate large amounts of data. This is foreseen in this general system architecture. Based on historical data, it is always possible to generate detailed perceptions into past events by using advanced machine learning techniques. The top level includes the visualization of the collected and processed data. It includes predictions and actions suggestions. The integration of geographic information system and usage of remote sensing tools and data provides a rich integration of information from in situ sources with the data from satellite sources. The proposed architecture of a water quality and quantity data collection and analysis system is represented here. It may be divided into the following types of data processing subsystems: data collection, data transmission, and data management, which includes storage and high-level processing. The data collection subsystems are the water quality module, the water quantity module, the evaporation module, the weather station module, the manual data sources input, and geographical information system. The water quality module includes the most used sensors for physical and chemical water quality parameters, namely total dissolved solids, dissolved oxygen, turbidity, water temperature, oxidation and reduction potential, potential of hydrogen, and electrical conductivity. Water pressure is included and relates to the depths of the parameters the parameters are measured. The evaporation module collects the water level variation in a Class A evaporation pan and refills the pan with water when needed. Evaporation depends on the meteorological conditions obtained by the weather station module, which collects air temperature, air humidity, precipitation, wind velocity and direction, luminosity, and UV radiation data. The data from these modules relates to the data to the water quantity module. There are two types of low-power wireless data communications in the system: short distance between local system components, long distance using LoRa between sensor nodes and gateway. Sensors from the weather station are placed some meters away from the microcontroller or single board computer unit, and their data is captured and decoded with a software-defined radio package installed there and afterwards sent to the LoRaWAN gateway. The low-power long-range wireless communication is based on the LoRa hardware and LoRaWAN software protocol architecture using the open-source KIRP stack. The LoRa gateway forwards the data through the 3G 4G network using an MQTT broker to publish the data and exchange control data with a LoRaWAN network application server. The data storing app subscribes the MQTT broker for all the topics from the sensors and stores the information using the database management system-based server. The latter is a relational model-based server with geographical data representation extensions. Geographical information system uses the data from the sensors and geographical information data, like maps and remote sensing information, to enhance the data analysis capabilities. The Node-RED data monitoring and visualization system provides a real-time view of the status of the sensors. A non-corruptible data image is maintained using blockchain storage, as critical data is kept by this subsystem. The most complex subsystem in the architecture is the data analysis system. A large set of tasks are assigned to this system, centralized around a Python-based web framework. The system takes the data from the database server and uses machine learning methods provided by common Python packages to provide high-level analysis to the users. This system also incorporates geographical data analysis with a Python-based API for the geographical information system. Concerning software, crucial concepts are the adoption of open source software to lower the cost and allow better control and integration of the overall system. Easy to deploy, maintain and scale services by choosing a container-based technology approach and a consistent programming environment with the Python programming language. Data collection with the support of a LoRaWAN stack stored with a relational database with geographical extensions and visualized with help of a web framework. And due to the critical nature of water data, an external blockchain technology system for data storage and sharing grants that the data is immutable. Additional visualization using Node-RED is also provided. The use of modern pattern recognition systems, machine learning and artificial intelligence software to predict problems is also a major aspect of this system. It is important to stress the integration level that it is achieved by the geographical information system, connecting the water and weather data collected by the hardware to the data introduced from other georeference sources. The concrete implementation of cost-effective devices under the framework of this general architecture is underway in order to build a complete prototype of the proposed smart IoT system for water monitoring and analysis. Future work includes the testing of the prototype on location to begin the initial deployment of the whole system. The use of modern pattern recognition systems, machine learning and artificial intelligence software, together with techniques to guarantee the reliability of the information, will provide a dynamic, easy-to-follow insight into the evolution of water quality and water quantity, and the consequences of climate change and other human-related activities, such as pollution sources. Thank you for your interest, and I will be happy to answer all the questions you might have.